All right, so last time we introduced Newton's second law, was it says that F equals ma, or the net force on an object is equal to the mass of the object times its acceleration. And now we're going to look at Newton's second law and this concept of what's called weight. So before we get into this too far, go ahead and try these three true-false questions. I'm just kind of trying to warm up your physics muscles here and things you've probably heard before in another science class. But try these three true-false, hit pause, and when you come back, we'll be here. All right, so hopefully you had a chance to try these three true-false questions. Number one says, true or false, if a person has a mass of 78 kilograms on Earth, their mass will be the same on the moon. And that is true. And we're going to talk about why that is in a second, but your mass doesn't change depending on where you go. So your mass on Earth will be the same as your mass on the moon. True or false, a person weighs less on the moon than on Earth. That is true. A person will weigh less on the moon than on Earth. So if you weighed something on the Earth, when you go to the moon, you're going to weigh 1/6 actually as much. And that has to do with the gravity, the acceleration from gravity that's on the moon. So if you want to feel like you weigh less, probably the fastest way to do it is go to the moon where you're going to weigh 1/6 as much. True or false, if a person weighs 600 pounds on Earth, then they will weigh only about 100 pounds on the moon. And I kind of just gave away that answer in my previous one because I wasn't looking a question ahead like I should have been. But that'll be true as well. So whatever you weigh on the Earth, you're going to weigh 1/6 as much on the moon. So if you weighed 600 pounds on Earth, you're going to weigh 100 pounds on the moon. I weigh about 200 pounds. Okay, 216. So 216 divided by 6. So if I went to the moon, I would feel like I weighed 36 pounds. Which would be pretty cool because it'd jump a lot higher if I weighed 36 pounds. So you should have said true, true, true. All right, so why did we answer the questions the way we did? Well, we have to look at kind of the key difference between mass versus weight. So in your notes, let's just jot down the definition of mass. Mass is the quantity of matter or stuff that makes up an object. And the units that we use in physics are kilograms. Now, if you took chemistry last year, a lot of times you're using grams. And the reason for that primarily is because you're kind of on a smaller scale. In physics, we tend to use the units of kilograms as our SI unit. So mass is going to be in kilograms. It's the matter that's present in an object. So if you think about every object is made up of protons and neutrons and electrons. And if you add up the mass of all those things, that's what gives an object its mass. So the quantity of matter or stuff does not change when you go to the moon. So Mr. Laurent here, I have all my protons, neutrons, electrons, and they have their masses. When I go to the moon, it's not like I lose protons or electrons or neutrons, hopefully, right? So my mass is not going to change. It's going to be kind of a fixed number. Your weight, on the other hand, does change. And we'll say the definition of weight is the downward force an object feels due to the mass it has. A more massive object will feel a stronger pull towards the Earth. And the units for your weight that we use in physics are going to be newtons. But in everyday life, for weight, as a force, we use pounds. And so newtons is what we use in physics. Pounds is what we use kind of in everyday life. So you might be asking yourself, is there an equation that relates mass and weight? And yes, 100% there is an equation. So we're going to give that to you in the next slide here. But take a second, jot down the definition of mass and weight here. All right, so we have to talk about what is weight mathematically. So according to Newton, this is just kind of basically an extension of his second law. So weight is going to be measured in newtons. And I'm going to go with a pen today. So weight here is measured in newtons, which you remember back to Newton's second law, that means that weight is a force. So I'm just going to say, well, this is a force. And then mass is measured in kilograms, so there's m. And then the value for gravity, acceleration from gravity that we're going to use is our 9.81 meters per second, which means that's the acceleration. And now here's the deal. Your mass, this never changes. So that's always going to be fixed like we were saying. You add up the mass of your protons, neutrons, and electrons, the stuff that makes you up, it's always going to be the same. But what does change is the gravity or acceleration due to gravity of the planet that you're on. So on Earth, it's this. But on the moon, it's 1/6 as strong. So if gravity were to change, when that gravity acceleration acts onto this mass, that means your weight will change. So if you want to shorthand this equation, just W equals mg. So a nice little fun calculation. If you convert your weight in pounds to mass in kilograms, we can kind of do a little fun calculation. So just take your weight in pounds. And I put a note here, there are 2.2 pounds in 1 kilogram. So what I did with my weight, I weighed 216. So 216 divided by 2.2, that means I'm 98 kilograms. So my mass is 98 kilograms. So that's my M. So I just took my weight in pounds, divided it by 2.2. And now if I multiply it by G here, so times 9.81, that means that my weight is 963, and just rounding here, newtons. So take your weight in pounds, divide by 2.2, that'll get you your mass. And then if you multiply by 9.81, that'll get you your weight. And then if Mr. L weighs, I was going to have you work backwards here, but if I weighed 963 newtons, how many pounds would I weigh? So you can kind of reverse engineer the process, but I already told you I weighed 216 pounds. But you can kind of see why in America here we didn't switch over to using newtons on our scales, because it's tough enough sometimes to see numbers that maybe are bigger than you want or smaller than you want. And you can see that the newtons, as far as the scale goes, it's bigger. It's going to make your weight seem bigger, even though it's the same weight, just different units. And a good conversion, or a good way to remember it is, I remember that a quarter of a pound lb is equal to about 1 newton. And we'll say close enough. It's just a quick estimation. So just think if you went to McDonald's and order a quarter pounder, which is literally 1/4 a pound, right? So if you ordered a quarter pounder, if you wanted to be in physics units of SI units, you could go to McDonald's and order a Newton burger, because a Newton burger would be the same thing as a quarter pounder. So roughly the conversion, because if I'm 216 times 4, that gets about 864 newtons. So it gives you just a little quick estimate. And like I said, it's just an estimate. But yeah, maybe don't do that at McDonald's, because if you did that, maybe they'd be confused in the drive-thru and it'd slow everything down. So you don't want to slow down the drive-thru. Well, I will say one thing about this. Somebody out there at home might be wondering, hey, Mr. Ent, I noticed you put gravity as 9.81 meters per second. In our previous units, we'd always throw a negative in there. That's a very good observation. What we tend to do with this is, because we know that weight always acts down, when we do this calculation, and I'm saying 963 newtons, and I know weight is a force, which means it's a vector, I would have to say something after this like 963 newtons downward, or I would say negative 963 newtons at the very end to indicate that my weight's going down. So that's a good observation. That's what we got for today. So when we go to our next videos, we did the first law, we did the second law. When we go to the next video series here, we're going to be on to Newton's third law. So the trilogy will be complete. So we'll stop there, but thanks as always for watching. Have a great day, Physics All-Stars.